started or mostly finished or made some progress on a homework assignment which was officially due the last class, but because of the hurricane, you finish it sometime before you sleep today. If you're having trouble getting into web assignments, you let me know so we can work around it. There's a few people that had issues where they try to log in and instead of being asked for their Blackboard password, they're asked for their WebAssign password. That's, according to WebAssign, that's due to the fact that you don't pick WebAssign's cookies. So you have to turn cookies on in your browser. I'll tell you that. Or you can just sign in through WebAssign. Any questions or issues or stuff? Yeah.
Is there a way to see if you correctly submitted your homework?
Did you? So on your homework,
I pressed submit.
There's a little green check next to the question.
No, I mean like in total. Like I press submit homework.
It submits as you go.
Okay.
So when you put in, when you see a red X, then that means you submitted it, but it's wrong. If you see a little green check, then you have those points. So it's not like you do your homework, you work on it, whatever. Okay, turn it in. It gets turned in as you go. So when I said that some people are working on it but have started it and some people have finished, that's because I can see that, you know, there's some people who have, I don't know, a point and a half. That means they got a question right and one question wrong and then right, and that's all they've done. So they may very well have 19 points by the end of the day. Okay? Other questions? Yeah? No, the paper homework is due next week, and there's no paper homework due this week. No, it says the 14th, the 15th, or the 16th. So, I put the homework on the week that corresponds to the material that's on the homework. So it's not on the week that it's due, it's on the week that it's assigned. So for example, homework 2 on WebAssign is up, and it's on this week, because it's due next week. So, yeah. And also there was some confusion, I know I announced this before, but sometimes people don't listen or it doesn't sink in, that if you do your homework problems more than 48 hours before they're due, you get extra credit. So it's quite possible for somebody to get a point and a half for a problem, because for a problem that's worth 1 point. So there's a lot of people, first homework assignment is worth 20 points, but there's a lot of people who have more than 20 points because they did them early. Okay? Other issues, questions, anything? All right. Then let's no, that wasn't. Whatever. Okay. So let's do some math now. Okay. So we were talking about we talked about what the integral is, how it represents an area. We were focusing on definite integrals, which is something like this, which corresponds to this area. We also use in the process a similar notation without putting little numbers here. So this is a number. Putting little numbers here means a function. So this would be some function. Maybe, well, I don't need a constant there. So this is a function. Even though the notation is almost the same, this is a function. And we saw last time by the fundamental theorem that the derivative is f. Right? So this is an antiderivative. So sometimes this is called an antiderivative. And there's lots of them. So for example, this should be nothing new to anybody. So for example, if I write the integral from 1 to 2 of x squared dx, then this is 1/3 x cubed evaluated from 1 to 2, which is 8/3 minus 1/3, which is 7/8. If I write this, then this is 1/3 x cubed, and there are infinitely many of these. So I can add any constant here I like, so we usually write plus c. This is the statement that the derivative of this is this, no matter what c is. Right? Again, better not be anything new. Just reminding you of what's going on here. A lot of students are sloppy and they leave off this dx. This dx is very important because it tells you what you're integrating with respect to, but it also is something that's useful in calculating the integral, which is a lot of what I'm going to talk about today. So let me write something that looks almost the same. This, well, actually, let me just write that. So, can someone tell me what this is? You can't do it? I can do it. Yeah. Okay, so let's take a poll. There's an answer. B. You can't do it. And you in the back, you had a statement.
X squared z.
C, x squared z. Anyone else? Any other suggestions? Yeah. Okay. Okay, so I'm going to ask a quicker question now. It's that. Wasn't one I planned to ask, but what the heck? There are 5 answers there. Channel 41, as usual. I'm stopping you now. Stop. So in fact, let's just report 15% of the people think this. I should be able to remember. A smaller number, 8% think this. Big number, 28% think this. 6% and 41%. So 6% think this and 41% think this. Okay, this one's wrong. This one's wrong. This one's wrong. So it's one of these two. This one's almost right. Can someone tell me what's wrong with this one? Yes, I need a constant. So the right answer is E, because the right answer is z squared plus the constant. Why is that? This dz tells me that the thing that's changing is a z. It's not an x. So x is just a number, 43. So when I integrate 43 dz, the answer is 43z plus a constant. So this one is morally right, but wrong due to a typo. Probably the 41% of you, a lot of you, didn't realize the plus c, but you said, it's none of that crap. So you took that answer anyway, so it was sort of a free gift. But that's okay. All right. So it's important to remember not only as a clue to you what you are integrating, but also, as you'll see in a minute, something else that helps you keep track of what's going on. So this role, so in math, we don't write something if it's meaningless when we write notation here. Every little symbol in here tells us something. The numbers here tell us what our bounds of integration are. The big stretched out S tells us we're doing an integral. This tells us our function. This tells us our variable. We put a d in front of it so that we know that it's the differential of x. It's a rate of change. A dx is not an x, but they're intimately related. So all of these symbols here play a role. So one of the problems that a lot of students have, or a lot of people have in math, is this is not true in writing prose, in English, really in any language. Even a very efficient, compact writing language like Chinese, there's redundancy there. There's no, or very little redundancy here. Every little mark here on the page means something. We don't just draw them to make it look pretty. Every piece of that symbol means something. And so when you're reading math, what a lot of students do when they're reading math, they read all the words, and then they say, oh, there's some symbol about something, let's skip it. You can't do that. In fact, what you should do is, there's a bunch of words, let me skip them, let me look at the symbols. Oh, that's really where all the content is. There are words there to help you understand the symbols. But both parts are important. And there's a lot of redundancy in the words. So probably you could understand this whole lecture. So if you go home and watch the video and turn the sound off, you can probably still follow this lecture just fine. If you turn the video off and just listen to the sound, you're going to be confused. By the way, I'm sure you all know that I set up those stupid cameras in the back every time. These things I put on the class webpage so that you can look at them later. I don't know if you find them useful, but I do it. Okay. So, now I lost track of what I'm doing. Okay, so we have all of these little things meaning something. Now, one of the first goals of this class is to look closely at integrals. You know what integrals are from your previous class? Well, mostly, sort of. And now we're going to learn how to do a bunch of integrals. So this is the last lecture in our review. One of the main techniques of doing integrals. So we already see that if we have, so we know from before that, well, I wrote it there, that if we know the antiderivative, we know the integral, whether it's a symbolic one or a definite one. And so if we have something like the integral of the square root of x dx, actually let me just, so how many of you know how to do this? Okay, so I'm not going to ask it. So to do this, we think of this as x to the 1/2. And now we just remember the power rule for derivatives and we turn it backwards. So we increase the power by 1. So 1/2 plus 1 is 3/2. And then we have to divide by this new power to adjust for the fact that when we take the derivative, we want this to cancel that. And then we add a constant. So that's very easy. If we have something slightly different, so this is really morally the same question, but it's written in a different way that makes it look harder. We use kind of a trick to change our point of view to make this easier. And that trick that we use is we make a substitution. The substitution so that's what I'm talking about today. The substitution, what we do, we write this not in terms of this x, but in terms of a new variable that makes our life more convenient. Can someone tell me what that new variable is? Yeah. Oh no, it's u, but tell me what I want u to be. You can call it w, you can call it Joe. 3x plus 4. So I'm going to use w because you all said u. I don't care what letter it is. We let w be 3x plus 4 because our life would be easy if this looked like that. So we're going to let w be 3x plus 4, and then we just have now the integral of the square root of w dw, but I did it wrong. But in fact, let me leave the dw off. This is wrong. Why is this wrong? Yeah? I'm supposed to have a 1/3. So I'm supposed to have a 1/3 because when I change x a little bit, so if I change x from 1 to 1.001, w is going to change by 3 times that. W, if I increase x by 0.001, w increases by 0.003. So that's the statement that 3 times the derivative times the differential of w, sorry, brain freeze, 1/3. dw is 3 times however much x changes. Take the derivative of these things, only I write it in differential notation. So that says when I wiggle x a little bit, w wiggles by 1/3 that amount. So this is the same statement. You can solve this if you like. As this. And so here this is wrong because I left off the dx. The dx here is a real part of the integral. It actually represents something. This part transforms to that, but this part will transform to this. The dx becomes the dw over 3, and the 3x plus 4 becomes the w. And now this is easy. This is just the same integral I did before. So this is just 1/3, 2/3, w to the 3/2. The const can go inside or outside because it's an arbitrary number. If you multiply an arbitrary number by 1/3, you get another number. So that's fine. So we could write this as 2/9. And we go back here to terms of x because I made up w. Okay. Now again, this should be a review for anyone, for everyone. Is anyone confused by this at all? Have any questions? What I want to emphasize is that we need to pay attention not only to how the stuff inside changes, but how the differentials change. I guess a little more formally, what's really going on here is we're just writing the chain rule in integral form. So if we know that from calculus, or from the first semester, so we know that the chain rule says that if I have one function inside another function, and I take the derivative, then this is the derivative of the outside function, plugging in the inside, times the derivative of the inside function. If we want to write this in differential notation, this would also say, oh, I can say it like that. So that's the chain rule. And now let's just integrate both sides of this thing. So if I integrate, with respect to x, then it's still true. And here, my g is, well, in this example is w. You can use u, you can use Joe, I don't care. So this is saying I have a function with something written inside it. So f in this example is the square root, and g is 3x plus 4. And here, this g prime of x dx, this is a 3 dx, and which is the same thing as, I lost my, yeah, that's right. So that means that I have to write it in terms of w, I write it as 1/3 dw. go. Right? Yes? No? Blank? Coffee? Something? Okay, so this is just rewriting the substitution rule in a slightly more formal thing. Let's do another example. I had one in mind and I forgot it. Let's see. So suppose that I have the integral of e to the 5x dx, so this should be easy. So, what is this? Yes. This is 1/5 e to the 5x plus some constant. And here what I'm doing behind the scenes, I didn't write it down. If you don't see that immediately, then what I'm doing behind the scenes is I'm letting u be 5x, so du is 5 dx, which means that dx is 1/5 is du over 5. That's a 5. And so when I change this to that, then I have the integral of 1/5 e to the u du, and I just write it down because that's what I know. So if you can't just look at this and write this down, please put this intermediate stuff down until you get good at it. And most of you are maybe to that point where you don't have to write it down, but maybe not. Okay, suppose I have something like the integral of sine of x over 1 plus the cosine of x squared dx. What would be a good substitution to make? Maybe, yeah. Okay, so let's make this be a quicker one. I should substitute u equals sine x, a, b, u equals cosine x, c, u equals 1 plus cosine squared of x, d for another class. I should substitute for another class. So, the right substitution is one of these things. Let's see. Okay, so I'm going to stop this, even though there's people still madly punching their buttons. Okay, it's stopping now. So I'm stopping. Okay. Stop answering! Okay, here we go. Stop. Stop. Okay, so a small amount of people, about 9%, think this. They're wrong. Well, you could say, so this would be hard. You could do this, but it would be hard. In fact, you could do sort of all of them except, well, nobody chose this one. Okay, fine. So really it comes down to these two. If I make, so let's see what happens. When I try each one. So here I have the integral sine x dx over 1 plus cosine squared x. And if I make the substitution, u equals the cosine, let's do the 1 plus cosine squared first. So the most popular choice, but it's close, is 41 to 49%. So those are close. So if I make the substitution u equals 1 plus cosine squared, then du is going to be the derivative of this, which will be, well, that will die. This will give me a 2 cosine x times the sine of x dx negative. And so this is sort of the most complicated bit here. So this becomes, well, I have a sine x dx. I have a u here, and I have a sine x dx. Then I have this sort of, right? I don't know quite what to do with this cosine x business. I have sort of a cosine x left over that I don't know what to do with. Now I could work hard and try and figure it out, but this is so I sort of have minus 2 cosine x du, and I can't get rid of this. So maybe I can make this go somewhere with a lot of sweat, but I don't want to work that hard. So let's try the other choice. So I'm going to let w be cosine. And when w is cosine, dw is minus the sine dx. And that's good because I have sitting around here a sine x dx. So this is really dw, except I just have to make it negative. So when I do this, I see dw sitting there looking at my face. So that means that this becomes, the thing on top becomes dw, but it's negative. And the thing on the bottom becomes 1 plus w squared. Now this is an integral that probably you know how to do. You should know how to do. If you were sleeping when they did inverse trig functions, well then you forgot. But this is the arctan. So this is the arctan of w. And there's a constant here, but okay. And now w was cosine is negative. Cosine x plus a constant. So really answer B is the better answer, but it's not obvious. So one of the things about substitution is it's not completely obvious what the right substitution is. It's more obvious when you play with it a lot and get some background, but it's not completely obvious. So it requires a little effort and maybe sometimes a little bit of a wrong turn. But it's okay to make wrong turns as long as you eventually get right. Yeah?
There's a 3 next to w over 1 plus 3w squared.
Yeah. Maybe a 1 over root 3. So you're saying it's 1 plus 3w squared here. Okay, this is what I want to integrate. So here, I would make a substitution. The u is, well, see, I want this to look like 1 plus u squared. So I wouldn't make the substitution u equals 3w. I want u to be square root of 3w. Right? I want, that's the end. The w is not square root. Because now this looks like 1 plus u squared. So then du is root 3 dw, so I pick up a factor of 1 over root 3. dw is 1 over root 3 du. So this is 1 over root 3 arctan. Okay? Or root 3 w. Want me to finish writing it? No. Okay. So it's a 1/3 square root. Yeah. Yeah, I'm not saying this won't work. It's just hard. So really, B is not wrong. I mean, sorry, C is not wrong. I probably C is not wrong. It's just hard. So I just gave up here. And I just went, because I gave up. You could maybe make this work. But if I ask you to drive to Port Jefferson, or to walk to Port Jefferson, it's not wrong to go to Huntington first. It's just not really a good idea. You could maybe make this work. So in some sense, and maybe you could even make u equals sine x work, although I don't see how. So in some sense, there's no completely correct answer to this. It's just that the best substitution is certainly the cosine. Yeah. So substitution, and I want to emphasize here that by analogy, I said this before, I guess I'll use this word again. This differential form, or dx, or whatever we're calling it, so when we write this thing, which everyone always seems to forget, not everyone, but many people seem to forget, plays two roles. This dx, it tells us the variable, but it's also like a unit. It's telling us, when we make a substitution, it's telling us how to transform the substitution. So it acts like a unit or a measurement, units of measure. So by analogy, this is like, say, this one is like, the dx is like saying inches, or meters, or pounds. It's a unit. And when we transform it to some other units, when we write this function in terms of some other variable u, we have to say what the relationship is between the original quantity and the new quantity. And that's all the chain rule is saying, too. The chain rule is saying, if we measure, if our g is in feet, and we change it to inches, we have to multiply by 12. Now, sometimes in math, not so much in science, the difference in the units are not linear. Sometimes in science, so for example, when you're measuring an earthquake, the energy is related to the value on the Richter scale logarithmically. So the change of units there is nonlinear. But typically in science, and in life in general, most of the units are related by a linear relationship. Not so here, in fact. The linear ones you can do in your head. The nonlinear ones you gotta write down. Somebody had a question over here. You gave up. Okay. Is it you? No, you're not. Did you raise your hand? Somebody over here raised their hand, and I was talking, so I ignored them. And then, okay. Sorry I ignored you, and you forgot your question. And I forgot who you were, so we're even. Okay. So, right, so this one is a nonlinear change of variables. Did I have another one that I wanted to do? I mean, in some sense, all of the substitution problems are the same. Once you get the hang of it, you're done. So, and supposedly you know that already. So I think I'm not actually, well, okay. So the idea in substitution so you won't know, of course, whether it's a substitution problem or not. But when you're doing a substitution, you want to look for, let me call it u. So you want to let it be something, and the thing that you want to let it be is something that, number one, simplifies the integral but also number two, the derivative is laying around in some sense. And what I mean by that, so for example, in this guy, letting u be 1 plus cosine simplifies this integral, but the derivative is not here, nor is it easily made to be here. Letting u be cosine simplifies the integral to be a harder integral, but its derivative is right here. Okay? So, let me do one more example. And the homework that's due next week, well, no, sorry, you'll see. So, okay, so we have this thing laying around. There's not always a unique substitution, right? If I have the integral, let's do, suppose I have an integral like that, and I'm purposely not using x. I can't use u for my substitution, so I shouldn't use u. I'll use x, or I can use z, or whatever. I'll use x. So, what's the obvious substitution to make? Yeah. Right. So if I let u be x be u squared plus 1, then dx is 2u du, and I have a u du laying around. So that's good. And so then this just becomes the square root of x dx 1/2. And there's the 1/2 dx from the u du. And so this, we already did this. This is 1/2 of, what? No. Sorry. X to, so this is x to the 1/2, so this becomes the 3/2, and then there's the 2/3, and then the constant. So this is, the 2's cancel, 1/3 of u squared plus 1 to the 3/2. That's the constant. Right? Now, whoops. I don't see another substitution. Well, okay, so this example was a stupid one because I remembered the wrong example. This happens. What was the one I wanted to do? I don't know. That one. Sorry. I'm tired of it now. So, okay, so that was easy. This was an easy one. I should have done a harder one, but okay. So, a lot of integrals, in fact, most integrals, are attackable by this technique of substitution. So what if I have something, oh, I guess I need to say something about the bounds. Sorry. So I forgot that. Suppose I have a definite integral. For example, the integral from 1 to 5 of log of 2x over x dx. So suppose I have some integral like this that I need to do, for whatever reason. Then I can do this in two completely equivalent ways, and I prefer the first one, but many people do the second one. So let me do it both ways, I suppose, even though it's the same integral. There's an obvious substitution here. Someone want to tell me what it is? Right. So if I let u be the natural log of 2x, du, except for a factor of 2, is sitting around here. Actually, it's right there. Because I remember that the derivative of the log is 1 over x. So here, if I let my substitution be the natural log of 2x, and the differential is 1 over 2x times the derivative of 2x, which is a 2, times dx. And so this is just 1 over x dx, which is sitting right here. So this just becomes the integral of u du. And I did this last time, and some people objected. This says x is 1, and this says x is 5. We just don't usually write it. These numbers, if I write 1 and 5 here, this is wrong. Because this is saying u is 1, and u is 5, which is wrong. So, actually, let me do it the way I don't like first. So the way I don't like, I can write for myself x is 1 and x is 5. Then I don't forget. Now it's not wrong, it's just unconventional. So, because I have to remember what x is. But okay. So if I do this, then this is 1/2 of u squared between x equals 1 and x equals 5, which gives me, well, I have to remember what x was. X is the log of 2x. Sorry. No. U is the log of 2x. Thank you. So this is 1/2 log of 2x squared from 1 to 5. I don't have to write the x anymore because it's the same. And so this is 1/2 log of 10 minus 1/2, let me just write the 1/2 out there, log of 2, which you can simplify a little bit as the log of 10 over 2, which is the log of 5, if you want, which is the same as the log of the square root of 5, if you want. I don't care. They're all the same. So that's one way to do the problem, which has a lot of extra garbage in it. So what I think is a slightly more efficient and also mentally easier way to do the problem is to just forget about x once you change to u. It's really the same. So here I have the integral from 1 to 5 log of 2x x dx. Make the same substitution. And notice that when x is 1, u is the log of 2. And when x equals 5, u is the log of 10. I don't have to write this down, I can just think it. And so this becomes then the integral from the log of 2 to the log of 10 of u du, 1/2 u squared, evaluated from log of 2 to log of 10, which is just 1/2. Wait, did I lose a square? Yeah. I sure did. Why did nobody stop me? Okay, so this is all crap. I'll say something in a minute. Log of 10 squared minus log of 2 squared there. This one's right now. And this one needs to be adjusted. And this is garbage. Okay. Let me get rid of the parentheses. So now they're both right, and they're both the same. This way is a lot more efficient, in my mind. And it's sort of what you do anyway if you're working with units. Suppose you're doing something in feet, and you discover that it's easier to work in inches, you don't change to inches for part of your calculation and then change back to feet. You just leave everything in inches. The number's the same, we're done. So I've just changed to a more convenient measurement system and I just change everything. Okay? So when you're doing definite integrals, you can treat them as indefinite integrals, do it all out, and then plug in the end, or you can just change over. Just convert your mind to the new system. You get the same answer, or you get an equivalent answer, because you're doing the same thing. Okay. What about so I can do substitution integrals all day long, but I'm tired of them, and you probably are too. Suppose I have an integral that looks like this. Is there a good substitution I can make? So some of you know, and you're saying no. Some of you don't know, and you're just looking blank. Okay? But there's no good substitution I can make here. Well, I can't find a good substitution. So I have to be a little more clever. I want to transform this into something else. Now, when we came up with the substitution rule, we actually looked at the chain rule. Chain rule is an important part of differential calculus. There's another rule that you learn when you're learning derivatives that is extremely important, which is the product rule. We didn't use the product rule, but maybe the product rule will be our friend here. I can integrate that piece, I can integrate this piece. I would like to write this as, so this is not true. That is wrong. And if you try that, you fail. You're done. Go away. This is dumb. Don't try that because it's just wrong. But we can manipulate some kind of product rule. So let's remember the product rule, which is for derivatives. And we want to somehow get a product rule for integrals. The product rule for derivatives says that if I have one thing multiplied by another thing, and I want to take its derivative, well then, I can write this as the derivative. I know I'm mixing notation, but that's okay. The derivative of the first thing, this is not minus, this is minus, plus the first thing times the derivative of the second thing. Right? So maybe I can integrate this and get something useful. So if I integrate everything inside, this is certainly still true. So now, but remember I'm trying to do the integral of x e dx dx. And if I don't think of this as two things that I want to integrate separately, I could maybe think of one of these as being a derivative and the other one as being an integral. That is, when I integrate e to the x, I get it back. So I could have this, think of this as the derivative of something. When I integrate x, it gets more complicated. When I take the derivative of x, it becomes a 1. So I could restructure this guy to say that, well, I want this, Or no, I guess it's here in that one. Doesn't matter. If I have something like this, let me. Since I have an equal sign, I can subtract this over here. And this is easy. This is the integral of the product. I mean, this is the product. Because it's the integral of the derivative. Now, there's a more familiar form that many of you may have seen this before. That is, if we think of, and unfortunately, there's an unfortunate notational collision, if we call one of the functions u and the other one v, this says that the integral, let's let f be u instead, the integral of a thing times the derivative of another thing is the same as the product of those two things minus the integral of, that's right, this way. So I can transform, I can trade a product of something I can take the derivative of and something I can integrate into the things, and integrate that guy and take the derivative. Now, this is more, you've never seen this before, so this is called integration by parts. Maybe you've seen before, maybe you haven't. We will spend a little more time on it. Let me just do this x e to the x example, and then we'll call it a day. So in this case, if I let u be x, then du is just dx. And if I call this part my dv because I can integrate it, then when I integrate it, v is just e to the x. So this is not a substitution, and it's unfortunate that u is used typically for both substitution and for the parts of integration by parts. So that's the way it is. And so this formula over there tells me that this integral is now the product of this and this minus a different integral, the product of v du, this and this. But this integral is easy. So that made something that was hard into something a little easier. It takes a lot of practice to get used to picking out what's what, just like it takes a lot of practice to get used to picking out what's what in substitutions. This is not on the homework that's due Wednesday, so if you don't understand it yet, don't sweat about it. Okay, have a nice weekend. See you Monday.